Okay, today we're going to finish up chapter 13, proteins, and we're going to talk about special proteins called enzymes. Okay, enzymes are globular proteins. Remember we had fibrous and things like that, but they're globs, okay? And their job is to make things happen. They catalyze reactions without being changed themselves. Okay? So their job is to make a reaction happen, but they're not actually involved in the reaction. In other words, they're not a reactant or a product. When the reaction's over, they're still the same. But without them, the reaction wouldn't happen. Kind of like photosynthesis. You know, if you don't have that light, the first part of photosynthesis isn't going to happen. But the light itself isn't a reactant or a product. Okay? They act on a certain substrate. By that I mean it could be a muscle, could be a gland, it could be a hormone, it could be a foodstuff. They all are very specific. That's why we have so many. We have over 1 million proteins, and probably most of them are enzymes. Okay? The enzyme itself is unaltered in the reaction, but without it, the reaction doesn't happen. So sometimes they just write it above where the arrows are to say, you know, this needs to be added, like heat needs to be added or something like that. Okay? Enzymes are named after whatever they react with or whatever their substrate is, and they end in ase. So like maltase reacts with malt sugar, which is maltose. Lactase reacts with lactose, which is milk sugar. I mean, some people are lactose intolerant. It means they're missing the enzyme lactase and they can't break it down, so they have issues because of it. Okay? And then there's some enzymes that have common names. I don't know if you know a lot of enzymes, but again, if you see that it ends in ase, you know that it's an enzyme. Okay? Enzymes can make reaction rates happen extremely fast, like 10 million substrate molecules converted per second, or 1 every 2 seconds, or 1 every 10 seconds. It just depends on the reaction and what's needed. So they can be super, super, super fast, and they can be, you know, relatively slow. Okay, what happens is an enzyme, they call it an enzyme catalyzed reaction. Okay, it can be reversible, but it starts with what happens is the enzyme bonds, or there's a site on the substrate. It's called the active site, and it goes in there and it causes a reaction to occur. Okay, once you get the enzyme and the substrate together, it's called the enzyme substrate complex. That's not that complicated, I guess. But once the reaction occurs, then you get your product, and then the enzyme's released, and it's the same as it was before, so it can be used over and over again. I think this probably explains it better. Okay, so here's your enzyme, and here's your substrate. What'll happen is the enzyme comes up, and this is the active site. It connects on there. They fit together. Now the reaction happens, and this substrate, and again, a substrate can be a muscle, it can be a gland, it can be a foodstuff, whatever. Now it produces 2 products, but see, the enzyme is the same. So now it can do it again. It can add to another one of these substrates and do the reaction again and again and again. So the enzyme itself isn't changed, but it has to join with its substrate, whatever it's going to react with, and they connect together, you get your reaction occurring, and then you get your products. So now I have my products, but my enzyme can be used again. Okay? The substrate that binds to the enzyme, it has a pocket or groove. Again, that's the active site. They fit together, okay? If the wrong enzyme comes in contact, then it doesn't fit, okay? So the change occurs in the enzyme after bonding to the correct subsite. That's why it knows that it belongs there, okay? They fit together. It's an induced fit, okay? The substrate selectivity then is very important because there's a lot of molecules around, and it only works on a certain molecule. So that active site is very specific, okay? You don't have an enzyme that can react on a whole bunch of things. It only has one job. It can only work on one thing, and that's all it does, okay? And then what the enzyme does is it brings everything together and makes the reaction happen. So it's like a facilitator. Its job is to make sure that everything happens it's not directly involved. Like I said, it's not a reaction or a product, but without it, the reaction isn't going to occur. So like I said, it's like a facilitator. Its job is to get everything together and make the reaction happen. Okay? What it really does is it lowers activation energy. It lowers the energy enough so the reaction can occur. And we haven't really talked about much activation energy. If you're in my general chems, we've talked about it. But that's just the energy that's required for a reaction to happen. It lowers it to the point where it can happen. Sometimes the activation energy is so high that reactions don't occur. So enzymes lower that so they can occur. Okay? Some of the things that change enzymes, okay, so that they don't work. If you change the pH, you're going to change. If you look down here, and enzymes work at different pHs. Not all of them work the same. Most of our enzymes we want, like it depends on where they're at. If you look here, here's pepsin. Pepsin's an enzyme, and its optimal pH is 2. Well, where does that work? In the stomach. Your pH in your stomach is much lower. You have a lot of acid in your stomach. So it would make sense for it to be, you know, in this range, because you want, it's optimal means it's best. So it's best, where it works best is at a pH of 2. Well, that works good if it's in the stomach. Okay. Saliva, or salivary amylase, we talked about that. It breaks down starch into glucose. It works best about 7. Okay. Well, the pH in our mouth and our blood and everything is a little over 7, so that works out great there. So amylase is not going to work real great in your stomach, and pepsin wouldn't work very good in your mouth, but where they're at, they work well for the pH that they are. Here's temperatures. If you notice right here, the best temperature for enzymes to work is about 37 degrees Fahrenheit. I mean Celsius. 37 degrees Celsius. If any of you can know what that temperature is in Celsius, it's like 98.6. See the thing there? Okay. So most enzymes work best at a pH of 7.3, which is great because that's what our blood is. 37 degrees Celsius, like I said, that's 98.6 in Fahrenheit. So they work best at the temperatures that we're supposed to be at and at the pH we're supposed to be at. But again, you have some, like I said, that work in the stomach, like pepsin. Pepsin wouldn't be very good outside of the stomach because you can see at 7, it wouldn't even work. But when it's in the stomach, that works out great. Okay. So again, the enzymes are configured to the job they have to do. Okay. We have some things called enzyme inhibitors. And what they'll do is they bind to the enzyme and stop it from working. Now, enzyme inhibitors can be good things. Like, let's say you have some issues, medication issues, and you have a medication that stops certain enzymes from working. Let's say you don't want them to work, okay? It has something to do with maybe your blood sugar or something like that. So you can take medications that'll cause that. But then we have other things like drugs that do that, which we don't want them to do. And I'm not talking about prescribed drugs. I'm talking about illegal drugs, okay? So when you have specific inhibitors, okay, they make sure an enzyme doesn't work. They can do it 2 ways. They can be competitive inhibitors. In other words, what they do is they compete for the substrate. They block the active site. They get in there and then the enzyme can't get in there. And again, I have a diagram to show you this probably better. But what they do is they don't allow the enzyme to do its job. Non-competitive, they bind at another site, but what they do is like they change the shape of the active site. Again, the enzyme can't get in there. So when you take medications, if you have certain problems, maybe you have you need to take some inhibitors for some like chemical imbalances or something like that. That's what they do, is they change so that the enzymes don't work. And again, it can be a good thing, it can be a bad thing, you know. This shows it better. Okay, so this is normally what happens. We have our enzyme, it attaches to the substrate, it goes to the reaction, you get your products. All right. But what if we have a competitive inhibitor? Let's say this is another thing and it blocks it. So this guy, you know, there's nothing, they can't attach to each other. Okay. So this would be competitive. It blocks off the area and now the enzyme, it's blocked off and it can't join to the substrate. Okay. Here's one where a non-competitive, what it's doing is it's changing the shape of the enzyme a little bit. So the substrate can't get all the way in. So again, the reaction is not going to happen. This is non-competitive because it's not right at the active site, but it is still changing the shape of the enzyme. So competitive means the active site is different. So, it can't work. They both do the same thing. They don't allow the enzyme to do its job. Okay. And there's all kinds of things that can cause these. Okay. Like I said, medications, illicit drugs, and then you can denature them. Like I said, if you change the shape of the enzyme, then it won't work, like heating it. You can get things extremely cold. Enzymes will still work when it's cold. They just won't work as fast. And if they get frozen, they'll still work later if you thaw them out. But if you heat them, they're done for, okay? Anytime you heat an enzyme, it won't work, okay? Like I said, if you take the example of an egg, if an egg gets frozen, if you thaw it out, it's still an egg. But if you heat it, now you change its structure, okay? So changes in heat, changes in pH, just like we talked about with protein, denaturization. Well, it's the same thing because an enzyme is a protein, okay? But these are the different ways too that enzymes can be changed. Competitive is right at the active site, and non-competitive is changing the shape enough so that it still doesn't work. It doesn't fit the way it's supposed to. And I think that's it. Okay, so excuse me, we are done with